In topology and related areas of mathematics, a subset A of a topological space X is called dense if every point X in X either belongs to A or is a limit point of A. Informally, for every point in X, the point is either in A or arbitrarily close to a member of A. For instance, every real number is either a rational number or has one arbitrarily close to it. Formally, a subset A of a topological space X is dense in X if for any point X in X, any neighborhood of X contains at least one point from A. Equivalently, A is dense in X if and only if the only closed subset of X containing A is X itself. This can also be expressed by saying that the closure of A is X, or that the interior of the complement of A is empty. The density of a topological space X is the least cardinality of a dense subset of X. Density in metric spaces. An alternative definition of dense set in the case of metric spaces is the following. When the topology of X is given by a metric, the closure of A in X is the union of A and the set of all limits of sequences of elements in A. Then A is dense in X if. Note that if is a sequence of dense open sets in a complete metric space, X, then is also dense in X. This fact is one of the equivalent forms of the bare category theorem. Examples. The real numbers with the usual topology have the rational numbers as a countable dense subset, which shows that the cardinality of a dense subset of a topological space may be strictly smaller than the cardinality of the space itself. The irrational numbers are another dense subset, which shows that a topological space may have several disjoint dense subsets, and they need not even be of the same cardinality. Perhaps even more surprisingly, both the rationals and the irrationals have empty interiors, showing that dense sets need not contain any non-empty open set. By the Weir's approximation theorem, any given complex-valued continuous function defined on a closed interval a, b, can be uniformly approximated as closely as desired by a polynomial function. In other words, the polynomial functions are dense in the space C, A, B, of continuous complex-valued functions on the interval A, B, equipped with the supremum norm. Every metric space is dense in its completion properties. Every topological space is a dense subset of itself. For a set X equipped with the discrete topology, the whole space is the only dense set. Every non-empty subset of a set X equipped with the trivial topology is dense, and every topology for which every non-empty subset is dense must be trivial. Denseness is transitive. Given three subsets A, B and C of a topological space X with A, B, C such that A is dense in B and B is dense in C, then A is also dense in C. The image of a dense subset under a surjective continuous function is again dense. The density of a topological space is a topological invariant. A topological space with a connected dense subset is necessarily connected itself. Continuous functions into Hausdorff spaces are determined by their values on dense subsets. If two continuous functions f, g, x, y into a Hausdorff space Y agree on a dense subset of X, then they agree on all of X. For metric spaces, there are universal spaces, into which all spaces of given density can be embedded. A metric space of density alpha is isometric to a subspace of C, the space of real continuous functions on the product of alpha copies of the unit interval. Related notions. A point X of a subset A of a topological space X is called a limit point of A if every neighborhood of X also contains a point of A other than X itself, and an isolated point of A otherwise. A subset without isolated points is said to be dense in itself. A subset A of a topological space X is called nowhere dense if there is no neighborhood in X on which A is dense. Equivalently, a subset of a topological space is nowhere dense if and only if the interior of its closure is empty. The interior of the complement of a nowhere dense set is always dense. The complement of a closed nowhere dense set is a dense open set. Given a topological space X, a subset A of X that can be expressed as the union of countably many nowhere dense subsets of X is called meager. The rational numbers, while dense in the real numbers, are meager as a subset of the reals. A topological space with a countable dense subset is called separable. A topological space is a bare space if and only if the intersection of countably many dense open sets is always dense. A topological space is called resolvable if it is the union of two disjoint dense subsets. More generally, a topological space is called kappa resolvable if it contains kappa pairwise disjoint dense sets. An embedding of a topological space X as a dense subset of a compact space is called a compactification of X. A linear operator between topological vector spaces X and Y is said to be densely defined if its domain is a dense subset of X and if its range is contained within Y. See also continuous linear extension. A topological space X is hyperconnected if and only if every non-empty open set is dense in X. A topological space is submaximal if and only if every dense subset is open.